Hello everyone, welcome to Unacademy guys. So this is another video including a lot of important name reactions, and this time once again I have taken few name reactions which are very related to each other, and it would be very easy for you to remember them if we study them together. So the reaction is Wolf-Kishner reduction, and very similar reaction which include the formation of hydrazine are also the Wharton reaction, the Eschenmoser-Tanabe fragmentation. Okay, and we also have seen some very important previous year questions from these ones. So we are just going to continue with our study. So basically, first reaction that we study today is the Wolf-Kishner reduction. Most of you already know this reaction mechanism. It is very simple. Alright, so what do we get from the carbonyl? Basically, carbonyl reduction to methylene using basic hydrazine, just that. So we have to take care of basic, we have to take care of hydrazine. Alright, so this is the overall reaction, that you have a molecule, you have a carbonyl, let's say a ketone is being reduced by the basic hydrazine. So hydrazine in the presence of a base, and some of the times ethylene glycol is also given. So you know what is the ethylene glycol used for? Ethylene glycol is used to maintain a higher temperature because we are refluxing. Okay, so to provide a high boiling condition, that is why we have the ethylene glycol used as a solvent. Okay, then further you have the reduction, complete reduction of this carbonyl into alkane, into the methylene group, CH2 group. Alright, so first we are going to see the mechanism of how it happens, and then we'll apply the same mechanism to many other reactions as well. So let's talk about it quickly. So here comes the mechanism, guys. First of all, we have the carbonyl. Carbonyl is being attacked by a hydrazine molecule like this, and that is going to, alright, the carbonyl bond is going to open up because it is a nucleophilic attack on the carbonyl. It forms the OH group by accepting a proton from water. Since it is there in the basic medium, we can't write H plus over here, right? So it is from the water. Very well. Now ultimately what do you see is hydrazine is going to push away the OH further, and that forms the hydrazone. Alright, so it is the hydrazone that we are talking about, the hydrazone over here. Further, what happens next into the hydrazone is that one of the protons, you have two protons on the terminal nitrogen. Let's say this one. This is your terminal nitrogen, you have two protons. So one of the protons from the terminal nitrogen is abstracted by water, let's say. Alright, let me just show it to you over here only, that let's say it is abstracted by water. The bond falls up between these two nitrogens, and you have a, either you can write it as a negative charge, or you can also simultaneously grab a proton from the solvent. So it is the same thing. So ultimately I have written it in this manner. I have just directly made a carbon hydrogen bond. Okay. Now also further you see that still on the terminal nitrogen there is one more hydrogen that you have, and this could be abstracted by water like this, so that you get a nitrogen-nitrogen triple bond, and the carbon-nitrogen bond opens up. This bond can open up to give you a very good leaving group, that is nitrogen and a carbanion. Now this carbanion, after abstracting a proton from water, is going to give you your alkane. So even though the reaction happens, the reaction happens in the basic condition, and hence it through the mechanism you see it leads to the formation of the carbanion. So what are the similar reactions that we were talking about? Very soon we are going to discuss that. First, let's do a very simple example. So what is the simple example? Let's see. First of all, you have this molecule, for example, it is your diaryl ketone basically. So the diaryl ketone in the first step, that is 80% hydrazine, it is toluene microwave, and then 20 minutes 75% is the yield. That these are some experimental conditions which you don't have to remember. So it is going to first of all give you the imine, or let's say the hydrazone, because it is like the imine only. There are two hydrogens which are on the free end of the hydrazone, right? Like this. CO2Me once again. Alright, now further what happens is in the second step when you have introduced the base, this is what happens in option number A. This is the product in option number A. First of all, the hydrazone forms, and then the addition of a base removes protons one by one. That is, it is going to take away a proton from water like this. Okay, so ultimately, yeah, so you had the CO2Me group right over here. So what happens next is you have a nitrogen double bond, a nitrogen hydrogen single bond, and there it is, a hydrogen onto the carbon. So till now only one hydrogen has got introduced into the carbon, right? But once again you see that there is a base, right over here in the second step there is a base, and you have the proton removal further and the generation of a carbanion. The carbanion, let me just write AR dash double. Alright, the AR dash and AR, for example, this is the aryl group and this is the aryl dash group. For example, I'm just taking it randomly. Now this is your carbanion that you have. Now this carbanion is going to take away a proton from water and finally give you AR dash methylene group CH2 and aromatic group once again. So this is going to be your final product. So for example, if you started with this ketone, it is finally going to give you the product like this. Okay, it is finally going to give you a product in this manner. So this is the overall Wolf-Kishner reduction. I know that all of you know it already. Now why are we studying this? Because we want to understand the mechanism of two very important and similar reactions. That is, first of all, a variation is the Wharton reaction. What is the Wharton reaction, guys? It is the rearrangement, okay, or let's say the reduction of the alpha beta unsaturated ketone into allylic alcohol, as you can see, right? We start from here, we end up here. Alright, so it is starting from alpha beta unsaturated, alpha beta not unsaturated, I must write alpha beta epoxy ketone. Yes, I must write alpha beta epoxy ketone turning into allylic alcohol. So let's see how that happens. The reaction mechanism is very similar to that of the Wolf-Kishner reduction. Let's see. Okay, so first of all you have hydrazine. Okay, so in the Wharton reaction you have hydrazine, no other reagent. Hydrazine is going to, first of all it forms the imine, you know that already, or let's say the hydrazone it forms. First of all it forms hydrazone. Hydrazone internally has this possibility of the attack like this. There is one thing that I want to share with you, that this proton which is lost, either it could be lost to a water molecule, or it could be lost to another hydrazine molecule, or it could be lost to the epoxy oxygen, in which I write the cyclic mechanism. So everything is possible, right? So basically this proton is going to fall off and the double bond falls like this into the nitrogen, and yes, it forms a double bond, or ये जो double bond है, it is going to open up towards the epoxy side, so that the epoxy group opens up to give you a alcohol group like after protonation. Okay, so first of all that gives you something like this. ये देखो, you have a hydrogen still, and alright, so there is nothing over here, and there is O minus on this side and R2. So this is what you get. This is your intermediate, and further you know that one more proton could be lost, and that is going to give you the carbanion on the sp2 carbon, right? So there is going to be a carbanion on the sp2 carbon like this, and this carbanion further, after taking away a proton, now reduces to H over here. Alright, so this is our Wharton reaction, a simple rearrangement of the alpha beta epoxy hydrazone into allylic alcohol. Very similar to the Wolf-Kishner reduction. Many a times you won't even know the name of this reaction, but you will do the mechanism correct anyways. Okay, so this is your Wharton reaction. Alright, moving onwards, the reaction number 39. It is the Eschenmoser-Tanabe fragmentation. Once again, as I had told you, it is very similar to that of Wolf-Kishner reduction. Just that here we are not using simple hydrazine, we are using tosyl hydrazine, which we usually call it is the tosyl hydrazine, jiska the real name is sulfonyl hydrazones. Alright, or let's say the fragmentation of alpha beta epoxy ketone via the intermediacy of alpha beta epoxy sulfonyl hydrazones. So sulfonyl hydrazones are getting formed. Yes, very well. So first of all we have alright, we have something like this. There is going to be a double bond, a single bond, NHTS. Alright, there is the tosyl group. Okay, something like this. So you are going to get the alpha beta epoxy sulfonyl hydrazone, which you have got over here. Now this is going to further do the fragmentation, and that might lead you to this product. So let us quickly see the mechanism, what is happening over here. If you want, you can just stop the video and do it by yourself as always. Okay, so yes, what are we going to do is, ye dekho mechanism mein, first of all it forms the tosyl hydrazone like this, a carbon nitrogen double bond. It is a tosyl hydrazone. Further, by the presence of a base, one of the proton gets removed. ये double bond यहाँ आ गया, and the epoxy ring is going to open up. Alright, so if you want to do it directly, it's also correct. Otherwise, if you want to create a negative charge on this nitrogen, which is not going to be there for long, but that is also okay. Alright, so yes, you can also write it in this manner, that is also correct. Further, what do you see? Further, when the O minus falls back, you don't have any more nitrogen hydrogens left on the nitrogen, so you can't go that way. So the O minus that forms, it is going to give you fragmentation like this. Alright, tosylate is a good leaving group, tosyl group is a good leaving group, and you have minus N2 minus TS. Alright, and along with that you have a ketone and you have a alkyne into the molecule, and this is your Eschenmoser-Tanabe fragmentation. Why is it similar to the Wolf-Kishner reduction? Because it is it's using tosyl hydrazone. Why is it similar to Wharton reaction? Because once again it is using the alpha beta epoxy ketone. Okay, the products are different because yes, it is the only fragmentation reaction we have. Wolf-Kishner is reduction, Wharton is rearrangement. Okay, so hopefully all of you will remember a lot of these reactions. Three reactions in one video we have done today. The major product A and B in the following reaction sequence are. Now these questions are all CSIR NET previous year questions. And if you want, you can just try and stop the video and do this by yourself, and then you can answer in the comment section. Till then I am trying to do it. So basically guys, you have two rings over here. You have two rings like this. Okay, so you see that the first reaction is nucleophilic epoxidation. Yes, all of you know what is the meaning of nucleophilic and electrophilic epoxidation. That is when you are adding a nucleophile to the double bond. Alright, that is the peroxide ion that in the presence of peroxide, hydrogen peroxide and NaOH, or let's say NaOH, you usually form the peroxide anion. In the presence of meta-chloroperbenzoic acid, that would be transfer of the electrophilic oxygen. Okay, so it is nucleophilic epoxidation that we are doing over here. Here the oxygen attacks, the bond is going to open up like this. Now further, what do we see? That whenever you have this methyl group on the bold position, alright, whenever you have the methyl group on the bold position, you're always going to add the oxygen from below. Why does that happen? Because of the steric hindrance which is being caused. Alright, so you're going to add the oxygen below. Now this is where we have reached to our alpha beta epoxy ketone. there can be two possibilities now. Either there could be the Wharton reaction or there could be the Eschenmoser fragmentation. So further, you don't have tosyl hydra zone. This is what you have to remember about. Little bit of details, important details. So in the fragmentation you have tosyl hydrazone, here you have simple hydrazine. So if there is simple hydrazine, I'm just writing this part. So if there is simple hydrazine, that is only going to give you Wharton reaction. Alright, that is only going to give you Wharton reaction like this. There is going to be NH2. Okay, this is how it happens. Further, the loss of a proton one by one is going to open up this bond. And finally, guys, you are going to get something like this. Okay, so there is going to be an OH group. Along with that, there is a shift in the double bond like this, and this is going to be your product. This is going to be the product which is present in option number 2. Why is option number 3 and 4 incorrect? Because in option number 3 nothing happens to the epoxide. That is not possible. In the presence of an acid, nothing happens to epoxide, not possible. Then fourth option may you see that the stereochemistry of the methyl is below and the OH is above. How is that possible? Because methyl is already given to be above, right? This methyl already given to be above. There is huge steric interaction, and hence you will favor option number 2 as the correct one. Alright, what about option number 1? Here you once again have the reduction of the carbonyl, no touching to the epoxide, so hence it is wrong. Right, now we move onwards to another very good question from December 2017. So this question, guys, is very important and a very recent question from the Eschenmoser fragmentation. So what you can do is you can try and stop the video and then do this question by yourself. So simply, first of all, it is going to make the hydra zone intermediate. There is no hydrogen over here, so NH and TS. Yes, you do have a TS. Alright, so further you get something like this, one more of the hydrogen being taken away like this, and the epoxide ring opens up. So finally, okay, you don't have a double bond onto this side, so it is going to be OH. Further, so alright, the stereochemistry is not asked, so that let's not worry about it. So there is going to be a single bond, not this one, and this is O minus. O minus, when it falls back, it is now going to break this bond. Okay, just a second, let me just draw once again clearly. So it is your N, TS and a hydrogen. So one of the proton is being lost and you have the epoxide over here. You have the epoxide over here and the groups like this, in this manner. Okay, then further what do you see? The double bond opens up and opens up the O minus bond. तो ये हो जाएगा इस तरीके से. Yes, very well. And now when the bond opens up, it is going to give you this kind of a product, which is definitely present in the options. Okay, so this is definitely present in the options. We look at the number of or let's say the position of the carbonyl and alkyne. So it is 1, 2, 3, 4 and 5. On the 5th position from the carbonyl you have the alkene. So let's check. 1, 2, 3, 4 and 5. 1, 2, 3, 4 and 5. Okay, A and C are possible. 1, 2, 3 and 4. It is not possible. 1, 2, 3 and 4. It is once again not possible. Alright, now moving onwards to what is the next step. The first step is the Eschenmoser fragmentation. Okay, so it has been asked in the PYQ, so you will be able to do this now. Palladium catalyst, hydrogen palladium and calcium carbonate is going to stop the reduction at the alkene phase only, does not completely go to the alkane. So you don't have trans alkene reduction, you have cis alkene reduction. You have cis alkene reduction, and hence the answer is option number C. Okay, so there might be a little bit of a change in the position 1, 2, 3 and 4. थोड़ा सा position change है, which means that just one carbon is missing. So 1, 2, 3, 4 and 5. 1, 2, 1, 2, 3 and 4. Just one carbon is missing over here, otherwise the product is going to be option number C only. We don't have the trans bond, not at all, we just have cis. Yes, you have these functional groups separated by 4 carbons, but your answer is option number C. Okay, so this was a very easy reaction mechanism, and I hope that all of you did understand. And right now, guys, we have one more very good question. The correct sequence of reagents to be employed in the following transformation is. Very simple question. Now I want to know the answer from all of you, as I always do. That is, you see alpha beta unsaturated ketone system very well, and you want to generate alpha beta gamma delta. Alright, so you want to generate delta unsaturated system. Basically it's very simple. Which reaction you are going to use? Are you going to use the Wharton reaction, or you are going to use the Eschenmoser fragmentation? That is completely up to you, because ultimately, first of all, you need just to form the epoxide. Alright, so you just need to form the epoxide first of all. Alright, and then by the use of, let's say for example, tosyl hydrazone, because let's consider the Wharton reaction first. Like this. Okay, so the bond is going to open up, and that gives you alright, so it is going to give us something like this. It is O minus on the other side. ये हो गए 1, 2, 3, 4. 1, 2, 3 and 4. Alright, so it is a single bond chain, so it can rotate. Yes, now alright, have I written a carbon less? This is going to be an attack over the hydrazine, and yes, the hydrazine forms very well. Alright, the bond might move onto this side, or let me just draw this once again. You have an epoxide. Okay, very well. You have an epoxide by the transfer. Since it is an alpha beta unsaturated ketone system, it will not take the per acid oxidation. Not possible, not possible. It is only going to take H2O2 and NaOH. Alright, because it is the electron deficient alkene system. If that happens, you have this product epoxide. Okay, and then further you have the tosyl hydrazone. So one of the nitrogens is going to lose a bond like this, and that is going to open up the epoxide through a 5-member ring actually. Okay, now this is O minus, and the bond is going to open up on the other side. So 1, 2 and 3. Alright, 1, 2 and 3 like this, and the bond opens up in this manner. Okay, so if the bond opens up in this manner, there is going to be fragmentation. So there is going to be fragmentation now this time, and what is going to happen? See, everything else remains the same. Alright, everything else remains the same. You are just going to get a triple bond over here, and that triple bond, when it is reduced, so you have to be careful that what are you reducing this with. So if it is reduced with hydrogen, palladium and charcoal, that is going to give you a complete alkane, isn't it? If you are doing the same reaction in the presence of Lindlar's catalyst, that is going to stop at the alkene conditions only. Okay, so looks like that the answer has to be option number D, which is the Eschenmoser-Tanabe fragmentation. So it is extremely important to study all of these three reaction mechanisms. They are very simple. Alright, and yes, what you can do is you can just directly make an alkyne over here. Just count the number of bonds. Okay, so we are starting with 1, 2 and 3, and on the fourth one there is a carbonyl. Alright, so on the fourth one there is going to be a carbonyl. 1, 2, 3 and 4th, and 5, 6, 7 and 8. Alright, on the 8th position there is going to be a double bond which is going to come right over here. So you have already seen the mechanism, you can try that out as well. So D is your correct answer. And guys, now I will take a leave and I will see you in the next video. Hopefully you're liking this content. If you are already, then don't forget to like it and share and subscribe with your friends as well. And if you want to join Unacademy Plus subscription, that is where I am teaching full time, you can join me over there. Okay, and Jagriti S is the referral code which you must need to apply for getting some discount. Okay guys, so we will see you in the next upcoming video, most probably a name reaction video only. Alright, so bye and have a nice day.